Hello all, welcome to my channel. Today we'll be answering the question, why do batteries heat up? To answer that question, you first need to understand the ideal behavior of an voltage source, and then we'll look at the non-ideal or the practical behaviors, and finally we'll be answering the uh, question, why do batteries heat up, and other effects which are part of the practical battery. So let's get started. So whenever we speak about a battery, we are technically speaking about a voltage source. A voltage source is nothing but a device which maintains a constant voltage between two terminals in an electronic circuit. And even though most of us don't understand the technicalities behind voltage source, we still use batteries in our day-to-day life very often. Uh, right from our batteries in our mobile phones, uh, in the cars, in the remote, batteries have become a very important part of our lives. And one of the major issue with these batteries is that they tend to heat up. Uh, so to understand why they do that, we'll first see what a battery does. A battery in an electronic circuit is represented by this symbol, or they're usually represented by this symbol. If the time varying, they're usually represented by this symbol. So all of this represent a battery itself, and uh, a practical circuit may look like this. A battery with a certain voltage V connected to a load. This load can be any device, including your mobile, remote, or any other circuitry. Okay, the main work of an voltage source or a battery is to maintain a constant voltage between the two nodes of the load device. This model can be thought of as an ideal or theoretical model. Of a voltage source. The practical circuit or the practical battery is much more different than the circuit that I dropped previously here. So the practical battery can be represented as shown with an voltage E and an internal resistance Rs. This internal resistance should not be thought of as any lump component like the ones you see in the electronic boards. These Rs or the Rs here comes as part of the intrinsic property of the battery itself by the materials used in building them, and they are distributed throughout the battery. So they're not any single component that can be found inside the battery along with in the series to the voltage source. They are part of the battery itself. Similar to the previous circuit, this will be connected to a load, and we'll try to maintain a constant voltage V across the load, and the load will be drawing a current I. So as you can see, this current I will also pass through this resistance Rs, and therefore it will be dissipating a power I square into Rs, and this is the power dissipated as heat in the device. The one main thing that you need to observe here is that the Rs here is quite small. It will usually be in the range of 10 milliohms to 100 milliohms. But as you can see, in this term, the only constant is Rs. For a given battery, once it's manufactured, the Rs will be almost a constant. The factor that is going to change the power will be the I square component. If the current increases in circuit, power loss also increases, as you can see from the previous formula. So if the load tries to draw more current, there will be more power dissipation in the resistance. Even though the load is drawing a small amount of current, but the device is running for a long time, then the I square R losses for the given time will be more. So the this might be very evident in the practical situations as well, like when you're trying to charge your phone, and if you try to charge it for a long time, or if you try to charge it very fastly, the phone tends to heat up. That's because of the I square R uh, power losses in the battery itself. So along with this I square R losses, there are other effects that can be seen uh, because of this internal resistance. Let me try to explain that. And this is Rs, this is V voltage, or E with our previous convention, and we'll have a load here. So the voltage V here and the current drawn through the circuit is I. So the voltage V is nothing but E, the total voltage applied, minus the voltage drop across the internal resistance, that is I into Rs. So as you can see, the total voltage that is seen out, as you can see, the total voltage that is seen at the load is no more a constant and depends on the voltage drop across the resistance, internal resistance. If the voltage drop is more, then the voltage seen at the output also drops down. And as you can see, the voltage drop across the internal resistance is a function of the current drawn by the load. So if you have a load that draws large amount of current, uh, then the voltage across the load tends to go down, and this can be represented by a chart which I'll show. So if the current drawn is I here and the voltage across the battery is V, for an ideal voltage source, this should have been a constant irrespective of the current drawn by the load. But with increasing current, the voltage will also reduce. This is also one of the important effect that is seen in a practical battery. And the Rs here increases naturally with the age of the battery. So you might have observed that an old battery might be giving a lower voltage. That's probably because the Rs has increased and the drop across the internal resistance is more now, and therefore the final voltage across the load will be less. To summarize, uh, the main culprit behind the batteries heating up is the internal resistance Rs, and the power dissipated is nothing but the current through the load I square times the Rs. And this Rs also contributes to a voltage drop I into Rs, and therefore the total net voltage that will be available for the load will be E minus I into Rs. And as the battery ages, this Rs tends to increase. This will result in more power loss and also lesser voltage for the loads.